Here's a photograph. Here's the same photograph stored in 1/10 the data using JPEG. They look almost identical. Now here's what happens if we instead keep 1/10 of the raw pixels, a scrambled, dark mess. Same data budget, wildly different results. The difference is which basis we used. Today we unpack the linear algebra that makes that possible. Let's start simple. Take a signal P with 8 pixel values. Think of it as a vector in R8. The standard way to write P uses the standard basis. Each entry tells you how much of pixel 1, pixel 2, and so on. But we can choose any 8 independent vectors, W1 through W8, as a new basis. Then P becomes a linear combination, C1 times W1 plus C2 times W2, all the way through C8 times W8. Those C values are the new coordinates of P in the new basis. Here's the trick that collapses everything into one equation. Stack the basis vectors as the columns of a matrix W column. 1 is W sub 1, column 2 is W sub 2, and so on. Now the linear combination, C sub 1 times W sub 1 plus C sub 2 times W sub 2 plus and so on, is exactly W times the coefficient vector C, so P equals WC. One matrix equation captures the entire change of basis. Let's see it in action. Take W sub 1 as the column 1, 1, 0. W sub 2 as 1, minus 1, 0. And W sub 3 as 0, 0, 1. With coefficient C equal to 2, 1, 5 multiplying W times C gives row 1. 1 times 2 plus 1 times 1 plus 0 times 5, which is 3. Row 2. 1 times 2 minus 1 times 1 plus 0 times 5, which is 1. Row 3, 0 plus 0 plus 1 times 5, which is 5. So P comes out to 3, 1, 5. To go the other direction and recover the coefficients, just invert C equals W inverse times P. Every transform you've heard of, Fourier, cosine, wavelet, is doing this one calculation with a different choice of W. Solving C equals W inverse times, P sounds easy on paper. But for a megapixel image, W has 1,000,000 rows and 1,000,000 columns. Computing that inverse naively costs roughly n cubed operations, completely impossible. So we need a clever W where the inverse comes for free. That requirement leads to the first law of good basis design, orthogonality. When the columns of W are mutually orthogonal, the inverse becomes essentially the transpose, and the transposing is free, it's just relabeling indices. Two vectors are orthogonal when their dot product is 0. Let's check this on a Haar wavelet basis. Here's an 8 by 8 wavelet matrix with entries plus 1, minus 1, and 0. Take column 2 and column 3 and multiply entry by entry. Column 2 is the level 1 wavelet, plus 1, plus 1, plus 1, plus 1 in the top half, then minus 1, minus 1, minus 1, minus 1 in the bottom half. Column 3 is a level 2 wavelet, supported only on the top half, plus 1, minus 1, minus 1, followed by 4 zeros. Now form the entry-wise products. 1 times 1 is 1. 1 times 1 is 1. 1 times minus 1 is minus 1. 1 times minus 1 is minus 1. Then minus 1 times 0 4 times gives 0, 0, 0, 0. Add them up. 1 plus 1 minus 1 minus 1 is 0, plus 4 more zeros is still 0. So column 2 dotted with column 3 equals 0. They are orthogonal. And the same check works for every other pair of columns in this matrix. One subtlety. Orthogonality alone doesn't give us W inverse equals W transpose. We also need each column to have unit length. Column 1 of the Haar matrix has 8 plus 1 entries, so its length is the square root of 8. Other columns have length square root of 4, which is 2, and then square root of 2. Divide each column by its own length and you get an orthonormal basis. Column 1 becomes 8 copies of 1 over the square root of 8. Now W transpose W equals the identity, and the W inverse equals W transpose exactly. Transforming and inverting are both just matrix vector multiplies, blazing fast. Speed is solved, but speed alone doesn't compress anything. We need the second criterion, sparsification. A useful basis should pack the signal's energy into just a few large coefficients, leaving the rest near zero. Then we can discard the tiny ones and barely lose any information. The standard pixel basis fails badly here. Each coefficient is just 1 pixel. Drop 90% of them, and you literally delete 90% of the image. It goes black. A wavelet basis, by contrast, concentrates most of the picture structure into a small number of big coefficients. The rest are noise level small, safe to throw away. Let's compare these side by side. On the left, standard pixel basis, keep the top 10%. The image is mostly black holes. The other 90% of pixels are simply gone. On the right, wavelet basis, keep the top 10% of coefficients. The reconstruction is smooth, recognizable, almost indistinguishable from the original. Same fraction of data kept, completely different outcomes. And notice the key shift in thinking. We are not throwing away pixels, we are throwing away small coefficients. The pixels get rebuilt from the coefficients that survive. That's what JPEG does. That's what JPEG 2000 does. One misconception was killing. Changing basis does not change the vector itself. The signal P is the same arrow in space. We are only changing the coordinates we use to describe it. Same arrow, two different grids overlaid. On the standard grid, the arrow reads as 3 and 1. On a grid rotated by 45 degrees, the same arrow reads as about 2.83 and negative 1.41. Quick check, 2.83 squared plus 1.41 squared equals 8 plus 2, which is 10, exactly 3 squared plus 1 squared. The length is preserved, as it must be under an orthonormal change of basis. Also worth noting, orthogonal columns alone do not give W inverse equals W transpose. You need orthonormal unit length too. Without normalization, W transpose times W is diagonal but not the identity. So W inverse equals the quantity W transpose W inverse times W transpose. Close but not free. Normalize the columns and everything snaps into place. W inverse is simply W transpose. Zoom out. Every transform you've encountered, the fast Fourier transform, the discrete cosine transform inside JPEG, the wavelet transform inside JPEG 2000, is the same equation. C equals W inverse times P with a cleverly chosen W. The art of classical signal processing is designing that W to satisfy both laws. Orthogonal, so the transform is fast, and sparsifying, so the result compresses. This is also what's happening in disguise in modern machine learning. When researchers train neural networks to find good representations of images or text or audio, they're searching for the right W, a basis tailored to data that doesn't come with an obvious one. Same equation, learned instead of designed. Once you see P equals W times C, every algorithm in the compression world starts looking like the same idea wearing different clothes.